In this video, I will explain the calculation of active and passive soil pressure load, active and passive soil pressures, and also to calculate their resultant forces. There might be some errors in the document. I will try to explain them also, and if I encounter one of them, I will correct. Please, first of all, subscribe to my channel. I will put this document, the PDF version of the document here. This is my website used for civil engineering education and also for civil engineering applications, which serves to students and also civil engineering applicants, which are the engineers. Okay, let's start. To calculate the dead load of the soil, dead load is used to calculate, to design the foundation. The unit weight of the soil is only required. But to calculate the lateral soil earth pressure, active and passive earth pressure loads are also terms used to refer to this pressure load. To calculate these lateral earth or soil pressures, pressure and their corresponding resultant forces, the unit weight, cohesion and friction, internal friction angle of the soil is required. These three parameters are required as input parameters coming from the soil test. These properties of soil types are given in table 220, 221 and 222, which are taken from Turkish codes. But these tables constitute samples from which, as a sample and as an example, that these parameters are tabulated in local governmental or local country standards or codes. You will encounter with such tables, and you will take the soil unit weight and other parameters such as cohesion and friction angle from those tables. They are ready to use tables, or you can make your own tests, and from your tests you can obtain for specific type of soils where your retaining wall will be constructed. You can take samples, soil samples from those soils, and you can obtain those values from the test which you will perform in the laboratory. And depending on the values given in table 220, the values which are given for cohesionless soils, which are in general sand and gravel. And depending on those values and the condition of the soil on the site, you will obtain the unit weight and the friction angle of cohesionless soil from this table, or any other table you have to use in your own country. Here there are some explanations related to this table and the symbols given in this table. Here, this table is given for cohesive and inorganic soils. Inorganic soils, we want our soils are inorganic so that they can be used in civil engineering applications as fill material, for example. And this table is for cohesive and organic soils. As cohesive soil, we mean clay and silt, or silt soils, which includes clay and silt in addition to sand and gravel or central gravel. And there are also some explanations regarding this table. This soil is not used in civil engineering applications as fill material, but they can exist behind a retaining wall, and this soil type shall be held by a retaining wall. So their properties are required sometimes, and that's why their properties are tabulated. These values are for consolidated and undisturbed soil. For stockpiled soils, the unit weight and friction angle values given in this table, they are valid only if the soil practical compactness is at least 95%. So compact the soil. In this situation, soil cohesion is so much 0, This is soil cohesion corresponding to which is obtained by means of effective stress, which is obtained by using effective stress values of the soil. And this is the cohesion obtained in undrained condition of soil. And some explanations are also given here. As I said, I will put this document to my website here, the PDF version of it. And I want to repeat, please subscribe to my channel again. I need some support. Now let's learn how the active soil pressure load is calculated. We need the value of this active pressure load to design the retaining wall here. The general shape of retaining wall is given here. This surface is sloped, this surface is sloped, a general condition of this retaining wall, and the held soil is also sloped. Okay, and also tensile soil pressure developed here. It's also a general situation. So I use this figure because it depicts the general situation which might occur in real applications. So the general formulation to calculate the active soil pressure load is tried to be provided here in this document. Now here, this is the resultant force because of this soil pressure. It's oblique here, as you see. This might be also the condition. Here, the explanation of the symbols used in these two formulas. Here, PA, small letters, PA means the bottom value of the active soil pressure load, and the capital PA is its resultant force. Here in this equation and this equation, the used symbols has the definitions given here. Beta is the slope of the soil surface, as you see here. Small delta is the friction angle of the wall. It's shown by so, but instead of obtaining its value, to make a conservative calculation, it can be assumed as 0. This angle is the angle between the wall surface and the horizontal. But the wall surface shall be the surface which is in contact with the soil. Gamma is the soil unit weight. And soil cohesion, soil friction angle, which can be obtained from the test or from the ready tables, as I mentioned previously. Active soil pressure coefficient is calculated by this formula, and these two are explained right before. Now, if the soil pressure becomes negative, actually this is the bottom value. Instead of this, I have to write soil pressure, active soil pressure. This is a mistake. If it becomes negative, as it happens here, tensile pressure develops in this region, okay, in the soil. But since soil cannot bear to tensile stress, and the tensile stresses do not act upon the restraint wall. Okay. So the value of the tensile stresses are assumed as 0. If you can check if tensile stress occur or not from this formula. If HC has a positive value, from here we understand that tensile stresses develop in the soil. And if such a situation occurs, in this situation, in equation 2.6, instead of H, we will use H minus HC. But this equation does not change. Okay? And Ka is calculated by means of this formula. And so when you are obtaining cohesion and internal friction angle, you can take these explanations as guide. They can guide you. For sand or gravel, which are cohesionless soil, cohesion is 0. Friction angle is considered for effective stress situations. Okay. If your soil is soft clay or normal consolidated soil, the cohesion value shall be obtained from test under undrained conditions. Friction angle is assumed as 0, so these are cohesive soils. For excessive over consolidated clay, the cohesion is assumed as 0. So as friction angle, effective friction angle is considered. For silt, cohesion and friction angles differs from 0. Let me check if this is a cohesive material, consolidated clay. So cohesion is assumed as 0. Let me check if it is true or not. It's conservative to assume cohesion as 0 for over consolidated clay, conservative. Okay. So I have an example here, numerical example. There is a restraint wall. It holds the water as soil, which has the unit weight of so much. But the height of the soil is 6 meters, but the groundwater level starts after 2 meters below the ground surface. The cohesion and friction angle of soil are given. It's cohesionless soil, so it's a granular soil. Calculate the active soil pressure and its resultant force. Assume gravitational acceleration as so much. First of all, as you see, beta is the soil slope, it's 0. We can use this value conservatively 0. Friction angle of soil is given and cohesion is also given as 0. Actually, I can write here I can sorry, forget it. And this angle is the angle here. As you see, it's 90 degree. It's 90 degree. So we put these values to equation 27, this here. And obtain, it's very simplified because of there are a lot of zeros and 90 degree here. We obtain this value. And then using this formula is always used even if tensile stress is developed here in the soil. It's always valid. It is used with H. We also replace the values of H. You see here, let's follow the values, numerical values of the symbols here. Ka is obtained as 0.27. Gamma of the soil is, but now the active soil pressure is calculated between 6 meter and 4 meter elevations. Because the soil changes, here we have groundwater included in the pores of soil particles. Here we don't have groundwater. So the calculation of active soil pressure is divided into two. Now gamma is 22.5 and H is here in this condition 2 meters. C is 0, so the rest of the formula terms in the values are unimportant. And we have this value. So its resultant force is obtained by this formula, which is a well-known formula, the area of a triangle. We obtain its resultant value, and as you know, it acts from the 1/3 of the height, which is 2 meters. So it acts at this elevation. Since the soil below 4 meters below the ground water level, the buoyancy force of water acts to the soil. Thus, unit weight of that soil reduces. Its unit weight reduces because of the buoyancy force.
Buoyancy.
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 Buoyancy force. Buoyancy force. Okay, the unit weight of water is calculated. This is not the weight. This is the unit density of water. It's multiplied with gravitational acceleration, and the unit weight of water is obtained here because of the lifting force, lifting provided by the water. The soil weight reduces and comes to so much value. So in the same formula now we will use instead of 22.5 this here calculated value 12.69. Now this value is known from here. We will calculate this value. So it's calculated from here, this value plus this value. So this value plus this value, which comes from the triangular area formalization. So here instead you see we use the same coefficient, active soil pressure coefficient, but the unit weight of the soil changed. And phi is since it is the same soil, same phi is used. But again, since it's cohesionness, we have the cohesion value here 0. So we got this value. And the resultant is then calculated. The resultant is, as you see here, the area of the rectangle, 4 times 12.15. And this area gives the resultant force of triangular area. Or instead, from the The average of these two values, since its variation is linear, calculated by means of this formula. Here h is 4. Okay. So the resultant force is obtained. That's so much. Now here, only for the rectangular area, the resultant force is calculated, which is equal to the area of rectangular portion. And this 27.42 is obtained from the area of the triangular portion. You can understand from the calculations from here easily. And their places are, since the height is here 4 meters, the resultant force of rectangular area acts in the middle height. But the resultant force coming from the triangular area acts at the 1/3 of 4 meters measured from the bottom. Okay, and the elevation coordinates of the resultant forces are also provided in the figure. And also the groundwater pressure applies pressure, water pressure, and its resultant force to the retaining wall. This should be the retaining wall. And you see from triangular area and the geometric position of the triangle is 1/3 of this length. We have made our calculations and the values are given here. Finally, the total resultant force of active soil pressure and groundwater pressure is obtained by means of the moment equation written about bottom point. This point, zero elevation. Okay, so this force has a moment time so much. This force has a moment time so much. This force has a moment time so much, and this force has a moment time so much. So if you multiply the forces with their corresponding moment times, you will take the moments of them forces about point E, which equals to the moment of their resultant force times the resultant forces moment time. The resultant force moment time is denoted here with this symbol, and it's 1.97 meters. So the resultant force of all distributions coming from soil and water is so much. Let's say this is soil, and this is soil, low groundwater. Now, this example is taken from the soil mechanics book of Smith and Smith, and some explanation, additional explanations are provided so that the reader can understand it easier. Now, passive soil pressure load. Passive soil pressure is this situation. When you have also active soil here and a small amount of soil at the other side of the retaining wall. In this situation, you have to calculate also the pressure coming from the less amount of soil side. In this situation, the parameters used in the formulation are given here. Beta is again the slope of the soil surface. And here is also given as beta in this situation. And the distribution is something like that, triangular. These formulas are used to calculate the passive soil pressure bottom value and also its resultant force. And now this time passive soil pressure load coefficient is calculated by another formula given here. Now we have an example. To make it more understandable, I made two examples, one of which includes only active soil pressure load, one of other includes only passive soil pressure load. Now we have an example here. Soil type and symbol are normal consolidated clay and CH respectively. Consistency of soil is medium hard and the soil is above the groundwater level. Soil is above the groundwater level. So we will not calculate the water pressure acting to the retaining wall. Now the solution phase. For normal consolidated clay, the undrained cohesion is considered in the calculations, as explained in the important role, as I remember. And soil pressure is taken as 0. So this is normal consolidated clay. For normal consolidated clay, do we have normal consolidated clay? Yeah, normal consolidated clay. Use Cu and use friction angle as 0. Okay. For medium hard clay, using table 221, medium hard clay. Okay. We have undrained cohesion value, so I will take 75 and as unit weight 20. Yes. Okay. As you see, the surface slope of soil is 30 degrees given in the question. And in the question also, this angle is also given. And friction angle is 0. This can be taken conservatively as 0. So Kp is calculated from this equation. And from these two equations, we calculate the bottom value of Pp, which is the passive soil pressure, and its resultant force. So much easy. When you look, you will understand it. Here, there is an addition. If we have surcharge load on the soil, how we will take into account. The additional load or the surcharge load carried by retaining wall is referred to as surcharge load. Surcharge loads are induced because of highway loads. These are the wheel loads of the vehicles. Railway loads, these are the wheel loads of the train. Stored or stockpiled material weights on the soil. Weight of structures, a building can be made here. So the weight of this building acts as a vertical stress, and because of this vertical stress, soil pressure increases, which are on the soil held by the wall. If surcharge load is a uniform distributed load, as given in figure 2.6, generally it can be assumed as distributed load, an equivalent height of a surcharge load, as given here, is calculated using equation 211. Here Ws, the magnitude of the uniformly distributed load. So He is calculated using this formula. Then the value of Pu and Pa are calculated using equations 212, this equation, and 25. 25 was given here. Okay. And as you see, since this is a rectangular area, the resultant force coming from the surcharge load acts from this place, and other component resultant force coming from the soil, lateral pressure of soil, acts from this elevation, which is in the magnitude of h/3 measured from the bottom line. Okay, now here we have a numerical example. A retaining wall and the hold soil, or the held soil, given in figure 2.6, has a height of 6 meters. This h equals to 6 meters. For surcharge load of 50 kilonewton per square meter, Calculate the active soil pressure. The unit weight and friction angle of the cohesionless soil are 20 kilonewton per cubic meter and 20 degree. So the C cohesion equals to 0. The slope of the wall and the soil surface are 90 degree. This is 90 degree. Beta is 0 respectively. So first of all, HE is calculated, the equivalent height for the surcharge load by means of this formula, and it's calculated as 0.5 meters. Then KA is calculated, again using 2.7, the same active pressure load coefficient. This formula. And Ka is obtained. And from equation 212, we obtain this value coming from the surcharge load. And Pa is calculated again using active, which is previously shown for active soil pressure. Okay, this formula is employed. Again, it is cohesionless soil. 0 comes here. And then the resultant force values are calculated, as you see here, from the area of rectangular and triangular. And its place, its value, the total resultant force is the summation of these two values, so much. And by taking moment about bottom line, Pu times H over 2 plus Pa times H over 3, we calculate the position of the final resultant force. Okay. This is a manual to calculate the active and passive soil pressure loads, and in case a surcharge load is added to the soil pressure, the manual here shows easily how to include to the calculations its effect. Thank you very much. You watched me for your patience. I will put this document in a week here. And also please subscribe to my channel.